Okay, so last time we kind of talked a little bit about what we could get in a tight binding model, and then we said, okay, if we look at this non-interacting case, depending on what the bands are like, I could get a metal or an insulator, right? If there's a gap or if there's no gap. Do you agree? Depending on how I fill my system. That's great. And okay, that was the first idea. And then we really, I kind of hinted at that we might see some sort of connection if we look at a certain kind of eigenvector, and then there might be some vector bundle, and we'll get geometry this way. So today we're going to look a little bit. Sorry, we switched rooms because this is a lot cooler.
Go through all floors and try to find it.
That would definitely work. It would take a while. Okay. So, right. So today, hopefully, what we're going to do is we're going to introduce this, connection, say more precisely what it is, and maybe compute like one simple thing, and see how it might be related to anything. Okay, and hopefully after today, once we have this set up, we'll be able to do a lot more in coming weeks, and finally get to this idea of connecting what happens in some periodic system, what that would tell me about a finite sample. So we're not going to do that yet. For now, we're still going to stick to this kind of system with periodic boundary conditions, and so on and so forth. So let's recall some notation first. Do you agree? So maybe I'll actually do this over here. Recalling some notation. Because this notation is actually quite important. Because otherwise you get easily confused. So we had some lattice with periodic boundary conditions. Okay, and we had some unit cell, right? Which was periodic in some vectors, a1, an. So it was system was invariant under translations by some m dot a, where this is a1, an, and then these are this is in the integers. Okay. Good. So then we said, okay, I can label my states is like this using alpha m. So alpha type atom in m dot a unit cell. Whoops. Maybe actually this should be written in color. So this is some position space there. Okay, and then we defined using these alpha m atoms. We defined two possible bases. Do you agree? And the bases were as follows in momentum space, right? So we defined two of the following bases. So the first one was for the alpha type of atom, the vector related to momentum k was just the Fourier transform e to the I k dot m dot a of the alpha type of atom in the nth unit cell, and we're summing over all the unit cells. So this was the first kind of basis we defined. But then we also looked at the second possible basis, which we use the same notation but with like a little twiddle above it. And the only difference is, here we're doing a Fourier transform over the unit cell. Do you agree? So these are all the possible unit cells, whatever. But this alpha atom within the unit cell has some sort of position. Do you agree? And so all we do is we can add this position as an additional phase, tau alpha. So this is really just I multiply by e to the ik dot tau alpha the previous momentum vector that we had to begin with. So tau alpha is the position of alpha atom within unit cell. Okay. So we define these two bases, okay, from this one. And you can check that, okay, if this basis is orthonormal, then this basis will also be orthonormal. So that's okay. And in fact, I can, with an inverse Fourier transform, I can reconstruct the position basis from the momentum basis as follows. Okay? So this is just to not get entirely confused. Okay? And then we had our Hamiltonian, right? And the Hamiltonian had eigenstates. Do you agree? So then we said, okay, let psi k how do I say this better? Okay. I'm afraid I'm going to confuse notation with other notation that the book uses, and we will all get very confused. Okay, whatever. Let's stick with this. Let psi of k be an eigenstate of H, and so then the book, and we're going to stick to this as well. The book introduces the following notation: that in the basis psi of k, in the psi of k, I can write in terms of this basis or this basis, right? Because I know this has to be made up of things of the same momentum by Bloch's theorem, so I can write that vector in this basis or this basis. And so I get two sets of expansion coefficients. I can either expand that vector in this basis or in this basis. Two sets of coefficients. So if I expand it in this basis, the coefficients are going to be called psi. If I expand it in this basis, the coefficients are going to be called u's. Okay, that's it. So I have to sum over alpha, sum coefficients psi alpha k, and then the same vector I can write in with some other coefficients. Okay? And you can actually notice that the coefficients are going to be related in what way? How is, what is psi alpha of k going to be in terms of u alpha of k? What's the difference going to be? Yes, that's right. But hold on. Which side does it?
On the U side.
On the U side. Yeah, on the U side. Yeah. It should be with a negative. That's right. Because to make this into an alpha, it has to come out with an e to the ik. Good. So this will be e to the minus ik dot tau alpha. Okay. Do you agree? Okay, very good. So we've now introduced this all this notation because it kind of becomes important later on. And initially, when I was reading the book, I was very confused because I simply didn't understand what the notation meant because I skipped a part where it explained this, and then 3 chapters later, I was like, what is any of this at all? And it didn't make sense. Well, because I just didn't read anything, and I just started reading whatever's happening 3 chapters later. Okay, so very simple. These alpha type of atom in the nth unit cell, Fourier transform that get alpha k multiplied by a phase of where the position of the atom in the unit cell to get a twiddle, and then the eigenvectors of H I can expand in this basis. Okay. Yes.
When we sum over k, like what's the range? Is it the first proven zone? Or
Yes.
Overall k?
It's the first balance one. Because after that, you're just going to be adding the same things.
Yeah.
Well, actually, no. You don't have a sum over k anywhere here. And plus, this sum over m is also only over the sample. Only over the unit cells in the sample. And that's why you need this normalization factor of 1 over root n. This calculation is implicitly in a finite sample, but if you wanted to really do a truly infinite calculation, then okay, you'd replace this with an integral and whatever, it would work out. You take some limit and goes into it. Good. So now let's compute something, then notice something, and then we'll be done because I didn't prepare much more than computing one thing and noticing another thing. Okay? Well, actually, no. Maybe we'll do a bit more stuff than this. So this is great. Now let's try and compute something that we can think about. Do you agree? So out of all of these things that I've written, which thing will actually maybe tell me something about the physics of my system? You have 3 colors. You have yellow, green, and orange. Which one actually might have some physics that we might want to study? Orange. Yes, because orange are eigenstates of an actual Hamiltonian. So, something about what actually is going on in my system. And this is great. The first thing you might say is let's try and just study this. Let's try and study these psi of k's. Well, okay, that's great. But maybe I want to do something closer to experiment. I don't want to do something in momentum space. Suppose I wanted to do something in real space. Do you agree? And if I want to do a real space, how do I go from momentum space to real space? What do I do? Very simple. Yes, I do inverse Fourier transform. And so these are what are called Wannier states.
Is this the same Wannier and Kramer Wannier?
In what?
There's Kramer Wannier Dole. Is this the same Wannier?
No idea. Maybe not. So Wannier states. What do we do? So these are now going to be denoted with W. Wm. Because if I'm doing a Fourier transform, I need to kind of give an x coordinate now. I will define it like this: 1 over root n, and I will sum over all k, and I will have my phases with a minus this time, ik dot n dot a, times my eigenvectors. Okay? And so this really tells me something that I didn't have just from the basis before, because now the psi k's are some non-trivial linear combination of the alpha k's, right? And so we want to say, let's look at these Wagner states. They're going to maybe tell me about something in position space. This is actually not entirely clear. And, okay. So you can kind of see that this is going to, this Wagner state is going to be telling me something about something in the, around the mth unit cell, right? Because I'm, that's the kind of position thing that I'm plugging into the Fourier transform here, right? And so I want to compute something in position space. So let's compute some kind of expectation value, okay? What expectation value? So let's make it simpler. Well, actually, no, not yet. Let's compute some expectation value. And if I want to compute something in position space, the expectation of what should I compute? Of what operator? If it's in position space, I should compute the expectation value of the position operator, right? So just, yes.
Wait, I just have a question about the space.
Yes.
It's like if you expand it then in terms of like the alpha, like alpha k, don't you have like the EVIK thing cancels and plug it in?
Well, sure. If you substitute this to be this, and then substitute that to be that,
Yeah.
you'll get that the coefficients there are going to be like some Fourier transform of the coefficients here. So, roughly, yes, sure. And we will do this in just a second. So we want to compute the expectation of value of the position operator, and I'll actually call this. What does the book call this? I think the book calls this XM is this thing. I take the mth, the Wagner state in the mth unit cell and apply x to it and compute the expectation value, right? So this is kind of going to tell me, on average, if I use my eigenstates, I try and build something that's localized. Where is this localized thing going to be on average? Okay. Now, for people who are paying a lot of attention, or maybe read the book already, is this a necessarily well-defined quantity? Yes or no? Thoughts?
Probably not, because your K's are identified with many other more K's, and then you can also identify M's with many more M's.
Sure, that's roughly the idea. Well, not quite. It's simpler than that. This is not gauge invariant. As you may remember, if I have some states, each of those states I should be able to just multiply by a phase degree. And once we do this calculation, we'll see that this will actually depend on the phases a little bit. And so this on its own will not have too much physical meaning, okay? But despite the fact that this kind of center is not going to be gauge invariant, I will be able, if I choose the same gauge, I will be able to compare two different centers. And then that will become very useful information. Okay, but let's do the calculation and see what we get. So let's compute just the zeroth thing. And what I want to do, I just want to take this, write this in terms of this, and then expand the psi k's in this basis, and then the alpha k's I will write back in alpha m, and so I just want to, because what do I know? I know how x should act on these things. or at least heuristically, I can expect that X acts on alpha M by giving me the mth unit cell plus what? Plus what? Plus tau alpha, that's right. So you can kind of assume that all my orbitals are kind of nice and symmetric and they're centered around where the atom actually is. Or whatever that means, around where the atom is. Okay, and so we would expect that these would be eigenstates roughly of this. Or if not eigenstates, the expectation value will definitely be this of the whole thing. Okay? So it's maybe the better thing to do is do something like that. That would be the more correct statement. To not cheat anybody out, something like this, and then maybe something equals. So let's do this n, and then here I have a delta function. So if I computed the expectation value of the same state, then it's where the atom is, and if it was two different states, then it should be 0, because you can think of like the atom's well localized, and so if any two atoms are, if it's not the same atom, then where this atom is mostly 0, the wave function. Okay. So, good. Now, let's compute this. Okay. So I'm going to have a sum. So this is going to be 0. Okay, and now I just have to. Well, actually, let's do this step by step, and let's first write down psi of alpha k in the position basis, so life is a little easier for us. Separately, so yes. Actually, this won't be too helpful. Whatever. Let's just do the whole thing. I know what I'm supposed to get in the end, but I don't want to mess up. Okay, so I just write this out. I have sum over k and k prime, and I have psi of k, inner product x, inner product psi of k prime, and I can factor out this thing, and this thing is just going to be e to the first one's going to have a plus I k dot m dot a, sorry, I m dot a times this one's plus, this one's going to be minus k prime. Okay, and this has a 1 over n.
Isn't m 0?
Yeah, sure. And m is m is 0. That's
So you just drop the whole thing.
that's right. I should be able to just drop the whole thing. That's right. Wait, but then this is not quite what I want.
You might as well just compute xm.
Yeah, let's compute x on for now, because I want to use like the. Okay, good. If I do have this phase, right, then I now can get rid of. Oh, sorry, I have a sum over k, and I don't have a sum over m just yet, right? I don't. Good. Okay, now let's expand psi of k in terms of these things, and then alpha of k we can expand in terms of alpha of m. Okay, this is going to be a tad annoying. Okay, if I start making further mistakes, we will. Okay. I was hoping would be faster for some reason. Good. So I have psi of alpha k, psi of alpha prime k prime. This one has a bar. Good. And then I have now what? Alpha k x alpha prime k prime. Okay, and then I still have this phase factor. Okay, and this should really be m dot a to be more in line with what we've been doing before. Good. And now what I want to do, I want to replace these once again with these Fourier transforms, with this one, and hopefully then we'll get what we want. Okay, now I have 1 over n squared even. Was I supposed to get rid of, I feel like I was supposed to get rid of a sum somewhere at some point, but I think those sums will all disappear on their own once I go to position basis. Sorry, let me just double check that I'm computing the right thing. Oh, I see. They did it much simpler than what I did. Oh. I'm very sorry. That's okay. Is it okay? Sorry, just give me a moment. Okay, sorry. Let's. I should have looked at my note. Let's go back a few steps, and this will be done in one line. Okay. Let's just compute this. Okay. Omega m. I substitute this in, and then I'll substitute this in at the same time. So this is x applies to 1 over root n, sum over k, e to the minus ik dot m dot a. Okay, but then I have to sum over alpha, my psi alpha k, alpha k. Do you agree? Okay, I just wrote out what the W is. Good. Okay, and now I can write down what the alpha k is in terms of the alpha n's or m's. So I get x over root n k alpha n e to the minus ik m dot a, and now I will pick up a phase of this phase plus I k dot n dot a. There we go. I'm starting to see how things might cancel now. And then times psi alpha k times alpha m, right?
Yeah.
Alpha n, sorry. Because we had the m was from here, and so the n is from this side. Do you agree? Good. Now what I want to do, I want to do the sum, say, over what? What can I do the sum over? I can do the sum over k. I want to do the sum over k, but then no, I don't do the sum over k. Okay, I want to apply now x to this thing. Do you agree? So all of these things, they're just numbers. So I can pull x through this, and I should get this thing by our assumption. Okay?
Arden, shouldn't it be 1 over n? Not root n? Plus,
I think it's,
did you get another 1 over root
I get another, yeah, that sounds right. That sounds right, but, okay.
Like,
Sure,
there
maybe.
is-
It will work out in the end. Okay, I agree with you.
But I think in like your first line it is roots, but then because you're going from
Yeah,
alpha
yeah,
k
sorry.
to alpha n.
That's right. Okay, good.
Yeah.
So okay, I still have all of this, but now, so what do I have? I have psi alpha k e to the I k m dot a plus I m dot a. This is n dot a minus m dot a. Good. Times what? Times ma. M dot a plus tau alpha. Alpha n. Okay, there we go. And I have a sum over k, alpha, and n. Do you agree? Right, so this is just some number, some factor. Okay? Don't worry, we're almost done. This is maybe not the most exciting thing. But now what we're going to do, look, this is just a number. I can kind of factor it out. It doesn't depend it does not, this number does not depend on, sorry, it's not m here, it's n. Right? There we go. Okay? Good. And now you can say, hold on a second. On the previous board, which I like, what I want to do is I want to kind of sum this back somehow. So here I have an alpha k. Sorry, I want to be able to do the sum over k somehow, so that at the end I combine this into an alpha k state, so that I could then take the inner product with the other Wang state. But you know, this n is kind of in the way, so I want to kind of put it somewhere. And one thing I realized, wait a second, this looks really close to me taking a derivative of this factor, this phase factor, with respect to k. Do you agree? So now in this part of the calculation, I'm going to set m to 0 so that we're computing x0. Okay? And now I'm going to realize the following clever thing, that my x0 is equal to 1 over n, sum over k alpha n, of what? Of psi alpha k, and what do I want? I want, so this thing is right now just e to the I k n dot a. Because I set m to 0 because I said let's compute this 0. Okay. And look, here, this is almost this looks almost like taking the derivative of just this exponential with respect to k. But what's missing? What's missing is this tau alpha piece. Do you agree? What's missing is this tau alpha piece. How can I get this tau alpha piece? Where can I get it from? Yes, that's right. So see, these are psi alpha k's. Do you agree? But we had from before that the where did I write? That the psi alpha k's were equal to, this has a minus sign. This should hopefully be a plus sign in the end, no? Oh, yeah, it will be a plus sign. So psi alpha k is this, like with a minus, the u alpha k, right? So what I'm going to do is I'm just going to write that. I'm going to say that, hey, this is alpha n u alpha k. Wait, I really want it to be with a plus sign. Why does it have a minus sign? Did I make a mistake earlier here? So if I have this is this, and this has this phase, then yeah, it should be with a plus, right? Because I have alpha k is equal to, oh, this is with a twiddle. So the non-twiddle should have,
Yeah, it should be a plus.
it should be a plus? Yes? Okay. So we made a mistake earlier, sorry. This should be a plus. Let's double check. If I expand, so the alpha k has
Because alpha
a
k
minus, so minus, yes, and so it should be plus. Okay. You can check this yourself. I've not convinced myself. Good. And so now, if I write this like this will now be ik n dot a plus tau alpha, alpha n, whoops, times this thing. Okay, you don't need to write this line, just write the next line. And so this is then just 1 over n, k alpha n, and then u alpha k, just times what? Just times the partial derivative with respect to k of this phase factor. Okay? Do you agree? But look, this over here, I have a sum over k. So, oh sorry, and I should also have a minus I up here. Right, because if I'm taking a derivative, I'm going to have an I come down, and then I want to have a minus I to cancel that. Good. And so we're very close to getting the connection finally. Okay. This is a k. Do you agree? Sum over k. And if my system is sufficiently large, whatever, I can turn this into an integral. Do you agree? And so the rule for these kinds of systems generally is, and of course I didn't write it down, but I think the idea is that if I have an integral sum k over n, this should be turned into, sorry, what should this turn into? 1 over like 2 pi to the whatever the dimension of the space is, integral dk, to whatever the dimensions. I think this is roughly correct, up to everything being wrong. And so I can write this as an integral now. So I still have the sum over alpha and n, but I now have this integral over k, e to the whatever. Do you agree? Now, you can see that the alpha n's don't depend on k, do you agree? But the u alpha k's do. And I can integrate by parts. Do you agree? I can integrate by parts. And I can argue that at the boundaries of k, you can show that these u alpha k's have to be periodic. So since the U alpha k's have to be periodic, the boundary conditions will go to 0. And so I can get that this is indeed equal to minus I over n, integral over, oh, sorry, plus I over n, integral over k, sum over alpha n, U alpha k. No, whoops. So now I have the phase factor, I have partial k U alpha k times e to the k n dot a plus tau alpha n. Do you agree?
You don't have the 1 over n
Uh,
because
oh, right, sorry. I now have the 2 pi.
yeah.
So the whatever dimension. But now, if I really wanted to, okay, and I will, well, we'll maybe do this, maybe won't do this. So you can see now that, hey, this thing depends on k, but it doesn't depend on n. So I can move the sum over n here, and this is going to turn back into a. This is going to turn back into my momentum vector. So this part is now going to be just a alpha kth momentum vector. Do you agree? So let me erase this part of the calculation. Sorry, this is taking so long. Maybe I should have just written the result and left the rest up to you. But where's the fun in that? So I get that this is equal to I over 2 pi sum over k, and then I do a sum over alpha times what? Partial k U alpha k times this alpha k. Do you agree? It's very good. And now maybe there's like a root n floating around somewhere here. Yeah, there's a root n floating around. And now, okay, maybe if I didn't want the root n, I would turn this back into a sum over k and kind of get rid of the, but maybe I don't want to do that just, yeah, I don't want to. Yeah. And now, if I, remember, I wanted to compute the inner product between, this state and this state. I computed what x on omega 0 is. That's just this state. Do you agree? That's just this state. And so what I could do now is, well, I just plug in the other state, and the other state is I can write in terms of the U alpha k's. So remember we had psi k was sum over alpha U alpha k's. Whoops, sorry. This should have a twiddle over. And this should, yeah, good. Was like this. Okay? So now if I expanded this other one in terms of these, right, I'll just kind of have U alpha k times alpha k with whatever integral up front. And this is just a number, this is just a number, these are orthonormal to each other, and so I will get the final result. Finally, we get to this point, after so much effort, that omega 0 x omega 0 is going to be I over some factor of 2 pi. I think I messed up the dimensions there a little bit, but that's okay. Integral over k, sum over the atoms alpha, is that right? Yeah. u alpha k times the derivative. So this would have like this. Okay. Very good. So we've done our first computation. Okay. So we get that if I look at my eigenstates and I look at the center of the mth of the 0th Wannier orbital, that it's given by this, interesting combination, this integral, over the coefficients in this twiddle basis. Do you agree? Okay. That's kind of interesting because, and so one thing, like how a lot of physicists write this, thing as, so I'll do this in yellow, so maybe a lot of physicists write this thing as like I over 2 pi uk times partial k uk. Okay. The problem is, don't write this down because I don't like this notation. Why do I not like this notation? Because when I write this partial k u alpha k, I'm being very specific in the sense that I'm saying I had some particular twiddle basis that I defined in some way. I wrote down some vector in terms of this basis. It had coefficients, and I'm taking a derivative of those coefficients. Do you agree? And so, in some cases, actually, I could write down this thing where I take derivatives of these coefficients, but I could also write down something similar where I'd be taking the derivatives of these coefficients. And actually, in some cases, it makes sense to look at something like this, where instead of the u alpha k's, you write the psi alpha k's. In other cases, it makes sense to write down the u alpha k's. But then, when you kind of write down something like this, it's not always clear, like, oh, which coefficients am I really talking about? And I don't know. It gets very confusing, at least to me. Yes?
Sorry, I just had a question on notation.
Mm-hmm.
The D for dimension.
Yes.
The dimension of what?
This is the dimension of the space where the lattice is. So it's the lattice, a one-dimensional lattice, a two-dimensional lattice, and so on and so forth. So this is maybe D, or this is D over 2, something like this. Okay. Good. Yeah. And so this thing is actually what people call the connection. So, this is going to be our connection. So in physics, people write it as just a number. Well, not good. So people write that AK, AI is equal to the sum over alpha, u alpha k, times partial ki, this has a bar, u alpha k. There should be an I here, over 2 pi a. Okay, there's definitely an I, but maybe the 2 pi appears elsewhere. This is our connection. And so what's the relation to the actual connections that, the like parallel transport connections that we talked about, the connection forms? So you can quickly realize that, this looks like what? This looks like I have hold on, let me think about this. Yeah. right, sorry, like what's the geometric idea behind this? I have my momentum space K, do you agree? And at every point, I have my Hilbert space, do you agree? And in this Hilbert space, I have some kind of chosen vector psi k, which is determined by the Hamiltonian because it's an eigenstate of the Hamiltonian. Do you agree? So psi k was something that's determined by the Hamiltonian because it's an eigenstate. Otherwise, I have a trivial vector bundle, right? Because I have coordinates for the whole thing using this basis. But here I can select specifically this one vector and kind of see how this particular vector changes as I go from, kind of one point in momentum space to another point in momentum space, right? At different points in momentum space, the eigenvector could rotate, right? For example, the common example is with the magnetic field, right? If I was to, if it wasn't momentum, but okay, actually that's more confusing, only more confusing. And so if you wanted to see, how does this vector change kind of relative to itself? Well, then precisely, this quantity that I wrote down earlier would be kind of like the thing you'd want to write down. This would tell you how the vector changes as I move it around, okay? And that's precisely what the connection tells us. And so that's in the sense in which this connection defines our parallel transport. Because I'm given some physical choice of like a vector that I want to study, and it defines some subbundle. And I want to see how this particular vector kind of changes as I change momentum. So roughly how to parallel transport it along my momentum space. And so it should be parallel transported like this because, well, that's just the derivative of by how much should the vector change if I move it a little bit. And okay, I define this to be my connection. Okay, let me think for a second. I have to find the... Yeah, okay. And so we get that if we integrate this connection over, so I was kind of not clear here because, I was not clear. This shouldn't work in d dimensions. I was really talking about a one-dimensional example because my connection is always going to be a one form. So it's something I will always want to integrate along like a one-dimensional path. And so I can only do this in one-dimensional, if my momentum space is one-dimensional. Sorry, I should have made that more clear. Okay, so the example that I've done this whole calculation in is I have the chain with whatever number of atoms and it's repeating, and I have some kind of hoppings. Okay, good. And I get that the 0th Wang orbital is given by integrating this connection over the Berlin zone. Okay, very good. And so now I'm going to kind of hand wave the idea of what's going to happen, and then we'll talk about it in more detail next week. So we computed this center to be this thing. Okay. And I said that this is not gauge invariant. And okay, if I kept those m's, you would see that it's not gauge invariant and depends on if I shift something. It doesn't matter. So what can I actually, what physical information can I actually extract out of this quantity now? Well, one thing that you can think about is as follows. So WCs are still some localized states in real space, hopefully. Maybe? And that's why we wanted to look at, where their position is on average. And so what you might want to do is say, okay, now suppose, before my system had, some hoppings, T1, I don't know, T2, whatever the hoppings were, right? So it depended on some parameters. Suppose I was able to rearrange my hoppings. Okay? I was able to change the hoppings with time. So I was able to somehow modify the physics of the system with time. And so maybe the electrons will favor hopping to one direction more or less over time. Okay? And so in that case, if I start changing, if the T1s and T2s start changing, the Hamiltonian starts changing, so the U alpha k start changing, because the eigenvectors start changing. Do you agree? And so then I could say, I could look at where, this means that the center of the 0th binary orbital also could potentially change. Do you agree? And you can roughly think of this as like, if I start changing some parameters in my system, then the charges can start moving around. Do you agree? And this is roughly this is kind of what it's telling you. It's telling you the position of some state. So it's telling you the position of some charge in the system. Okay. Good. So then, suppose there was some additional parameter that changed with time. So these became time dependent. And this thing became time dependent. Okay? And then I can look at the I want to make sure. We're at the.
Did say you had a meeting at
Yeah, that's okay. It's gonna run until 8:30, so I don't mind. We're almost done. Sorry. Right. So this is kind of the position of the charge, and so then if I started varying something in time, and then if I took the time derivative of this x0, this should roughly tell me how quickly is charge kind of moving out of this position. So I should be able to think of this as some current as some current. Is that right? Yes. Just as some current. Okay, and so now, using this kind of approach with the Bloch Hamiltonian, I realized that, okay, I did some computation, I got something that's not gauge invariant, but then maybe if I take the derivative of it, it will give me something that I can actually physically measure. And now in the book, they give a much more detailed explanation of why you can really think of this as the current. And actually, the more interesting thing is that if you had this at some time 0, and then, at some final time t, and subtracted it from some time, from some initial time, I think this is the change in polarization. And then they had like a fairly complicated discussion of why that's the change of polarization, and it's just, I don't know, it was confusing and very long, and I understood it for a few minutes, but I think this is kind of the simpler picture that you can understand, that, okay, this is kind of telling you where something is centralized, and if you take a time derivative, that would give you the current of how fast it's moving out of where it is, which I interpret as the current. Okay. So, yes. And so, okay, this kind of the derivative of the connection would give me something like this. Okay, and so this is the main idea that we're going to see next time with charge pumping, is we're going to try and take our system, right, start varying some of the parameters, additional parameters of the system, that's going to move my charges around, and I will try and do it, change my parameters in such a way that I change my parameters in a loop. So I change my parameters and then return it back to the same parameter. So I have some oscillatory external force, whatever it is, and that will, kind of pump, keep doing something to my system over and over again. And so this is what the system they call charge pumping, and we'll kind of see through this idea that I'll have charge flowing through my system because of this. Okay. Yeah. Okay. Well, let's stop here. This is